All right, wonderful. Hi everyone, thank you so much for coming. I'm very happy to see all the other papers, very excited, and I'll present my paper on the A/B testing problem, which is, this is kind of loud, so you can actually turn it off, which is co-authored with Alex Deng, who's at Microsoft.
Hey, never record it.
Oh, sorry.
You don't need to use that one, it's fine.
I'll just lower the volume, that's all right. Which is co-authored with Alex Deng, who is at Microsoft, and so is Glen, Weyl, Justin Rao, who used to be at Microsoft, but now he's at HomeAway, and Montiel, Olea, who's an econometrician at Columbia University. So experimentation is increasingly important to innovation in a lot of areas, and most famously for all of us, it's the A/B testing revolution, where if I go on my cell phone and I go on Google now, I'm going to be on like 10 experiments that are being used to make Google better and test all sorts of features, see whether they're good or not. And experimentation is done very differently in different places. So there's this big data approach, which is something that, for example, Google would do, which there's a lot of triage of the ideas that actually make it to an online experiment. And each experiment has millions and millions of users and it's very precise, and you try to get these very small effects. Versus this lean experimentation approach, which is a lot of startups do, which is try to do a lot of stuff with small sample size and see what works. And this paper is about how can we use scarce experimentation resources to improve things as fast as possible, so how do we experiment more productively. I'll answer this with a new framework, a new theoretical framework for optimal experimentation. And the key thing, in a lot of ways, the model is going to look a lot more like what A/B testing actually looks like in real life than, for example, Bandit problems. But then the key thing is going to be that I'm not going to assume, like we usually do in this literature, that you have these thin-tailed distributions of the effect sizes of stuff. I'm going to allow for very fat tails, and that's going to make a huge difference. And then we'll have an empirical application to one of the largest experimentation platforms in the world, for Microsoft Bing search engine, which probably a lot of you guys don't use Bing, but actually it's a real business with 600 million users and $7 billion of revenue, and actually 30% of people in the US use Bing. So let me just give a brief summary in a couple minutes of the whole paper. So this is a graph with data on a bunch of experiments that have been done to improve Bing. So you can think of this as all the experiments done to make Bing better over a certain time period. So the x-axis, each dot here is an experiment. So each dot here, there's this team of engineers that spent like months thinking about something and implementing it. They code it up. They put in an online experiment that on average those have like 20 million people. And then you saw how much better did that make Bing, and that's what I put in the x-axis. My figure starts from here, so I cut a bunch of stuff that's negative, but that's there too. But some stuff is good, some stuff's bad. The first thing that you see is that a bunch of points are going to be here, clustered around 0. And the reason why is that, sure, you have 20 million people in each experiment, but you don't have infinite people, so there's still a little bit of experimental noise. So all of these ideas here, sure, maybe they were kind of good, maybe they were kind of bad, but basically they didn't really do very much, and because there's this experimental error, you see all this mass of things here, and which you should expect to see because you're trying these thousands of ideas over time. Now, the thing that's really striking here is that some of these things were extremely good. So you see all these observations here that the best ones are actually like 10 standard errors higher than 0. So these ones maybe you just got lucky. But these ones, there's no way that you could have ever gotten lucky. Those are real big improvements. There's like this one thing that make Bing like 0.3% better or something like that, which is a lot in real life. And so not all those things are very big, but they're also very valuable. So there's a way to turn how much better you're making Bing into profit. But the most famous story at Microsoft is that there's this one experiment that people did called the long add titles experiment. That someone literally just made these strings longer that describe the ads. And for a long time, that wasn't taken into an experiment because people thought that it wasn't a very good idea. But then someone tried, and it turns out to increase revenue by like 13%. And so, sure, there's like this long ad title story, but there's actually a lot of these big outliers that are like that. So in this paper, we're going to have a model to figure out how should we be doing these thousands of experiments to make this idea, make Bing better. And there's going to be two main conclusions that are going to come out of the model. So first of all, you can use the statistics and the fact that you know the distribution to do a Bayesian correction for how big are the actual effect sizes given that you're trying a bunch of stuff. And what that's going to do is that The y-axis that I put here and with this right-hand scale is that for each dot, that's my Bayesian estimate, my corrected estimate of how good an idea I actually think that idea is, given the effect that I saw in the data. And so basically what that's going to do is that if there's something that's kind of mediocre here, sure, maybe it's like kind of statistically significant, but I still should hugely shrink that idea because I probably just got that because of experimental error. I probably just got lucky. But all of these big outliers here, like the long ad titles, they're real. You should shrink them very little because there's no way that could have happened because of experimental error. Now, the second thing that's going to happen more crucially is that the way that you should be running the experiments hugely depends on how fat the tails of the distribution of results are. And when you have very fat tails, which turns out to be the case empirically, as you can kind of see from this picture, then this big data approach is actually not at all the best thing that you can do. What you actually want to do is that you want to be flying everything that you can fly, and it doesn't really matter if that decreases your experimental size, because what you're doing is that you're just gambling to try to find one of these big outliers, try to find something like long ad titles. So that's what I'm going to do. And this is the model, how the model works. So this is what we call the A/B testing problem. So the idea of the model is that you have these end users that you can put in experiments, and you have I ideas, but you don't know how good each idea is, because there could be something that's really awesome, but you just think it's bad or something. So ideas have some quality delta I, which has some distribution G. You have an experimentation strategy, so the firm has to put users in different experimental buckets, and experiments are going to produce some normally distributed signal with some noise, and the variance of that noise is lower if I put a lot of users in the experiment for some idea. And then after I see the results of these experiments, I have an implementation strategy where I choose the ideas to implement, and my objective is just to maximize the sum of the expected quality of ideas that I implement. So this is, of course I didn't invent optimal experimentation. There's like 100 years of theory of optimal experimentation, most notably in bandit problems, which are the kind of canonical framework. And this is different in 4 key ways. So first of all, there's no exploration-exploitation trade-off, because in the bandit problem, if I pull one arm, I can pull the other arm. Whereas here, if there's one idea that's good, another idea that's good, that's awesome. That's just to both of them. Another crucial thing is that there's no dynamics. So in real life, the amount of batching that you can do on A/B testing is extremely restricted. The dynamics that you can do is extremely restricted because, for example, you have to run experiments for multiples of a week because there's huge days of the day of the week effects, and otherwise you get super biased results that are basically worthless. And there's also problems that if you let people do too much batching, they're going to kind of do p-hacking, just fish for good results. So in my model, I'll go to the extreme of having no dynamics, which I would argue is a much better approximation of how A/B testing works than for example, this fully unrestricted dynamics of the vanilla bandit problems. The arms are not substitutes. If I can implement 2 things that are good. Oh, sorry, what I meant by no exploration trade-off is that the value of an idea after it's implemented is so much higher than the time that it's going to get used that I don't care about not using my sample so that I could get more value or exploit more in this model. And then the key difference, there's all these differences that are kind of like making this more similar to how A/B testing actually works. But the key thing is that I'm not going to assume that the support of the quality is bounded or something like that, which is going to be crucial for the results. Now, okay, so let me give you a very broad outline of how the theory works. So it turns out that this problem is extremely tractable, and the way that you want to solve this problem is that you want to calculate something that's called the production function, which is take some idea, what's the value, what's the expected improvement that I would get on Deng if I just put data on that idea. So there's some mathematical definition of that I'm not going to kind of give it to you in algebra, but you can kind of figure out that if I have a lot of data, of course the idea is more valuable because I only implement it in the case that it's good. So the first thing that you should do once you figure out that what matters is production function is that before doing a bunch of math, just go on the computer and calculate some production functions. And so I did that in this graph, and then I did this for a bunch of possible distributions of idea quality. And so here's for a normal prior distribution of idea quality. And these ones are for T distributions, which are distributions that possibly have fat tails, and where I drew a bunch of different production functions varying how fat the tails are. And basically what you found is that for the normal distribution, you have a very convex production function, whereas for the T distribution, you have these extremely concave production functions, and that become more and more concave as you lower the tail coefficients. And they can be convex too when the tail coefficient is high, which means that when the distribution has thin tails. And so basically what that's saying is that when you have very fat, very thin tails, like in the normal distribution case, then it's kind of useless to run a small experiment because you wouldn't change your mind anyway if you just see some result in the experiment. So you have to run some big precise experiment to actually get you to change your default decision. And so in that case, what you want to do is that you want to run a few big experiments. Whereas in the case of fat tails, you want to do the opposite because you're basically gambling to try to find these outliers. So it's okay to run a lot of little experiments. So what the main theorems in this paper show basically is exactly that. I'm not going to mathematically state the theorem, but I'll give you roughly the intuition. So basically, if the distribution of ideas has sufficiently thin tails, and what matters is this number called the tail coefficient, which is a standard measure of tail thickness. So if this tail coefficient is larger than 3, turns out that 3 is the magic number, then this kind of big data experimentation approach is optimal. So in that case, it's kind of like the normal distribution, that the value of information is convex at 0 and has 0 derivative. And so there's this very increasing returns to scale to doing big experiments because you're not going to change your mind with a small experiment. And so you should strictly triage ideas, kind of like people do at Google and Microsoft and Facebook. And you're going to run few very high-powered experiments that can detect effects with very high probabilities. And so this is similar to our standard logic of doing power calculations and things like that. If the distribution has sufficiently thick tails, so if alpha is smaller than 3, then this lean experimentation strategy is optimal. And so the value of information is concave at 0 and actually has an infinite derivative. You have very decreased returns to scale. And you should fly everything, run many small experiments, do kind of like this startup lean experimentation approach, hope that you find a big outlier. And the idea is that, look, if there's a big outlier, you're going to detect it even with a small experiment. So you kind of want to go crazy and try everything. And if you want to go on my website, it's weird how 3 is the magic number. But actually, there's a very nice intuitive explanation that takes kind of 10 or 15 minutes to go over, but pretty, not like crazy math. But there's a good explanation why 3 is the magic number if you go on my website. Great. So I'll use the rest of my 8 minutes to, instead of talking more about the theory and giving all the results, which we can all look up online, I'll just talk about how this works in practice and show you some real data from Bing and see what are the implications of having these fat tails. So I'm going to use data from Microsoft EXP platform, which runs experimentation for Bing, and it started at Bing because experimentation is so much easier with cloud-based software that A/B testing was kind of invented several times over in these big cloud platforms, but now it's spread through the whole company. So EXP does experiments for Microsoft Office now, for example, too. So even offline software now uses experimentation. And I'm going to actually focus my data a lot in this study. So there's a lot of data cleaning that I'm not going to explain that much, but basically I'm going to focus on data from Bing, and I'm going to focus on data from the US. So the idea, and focus on certain areas, they're like the most mature areas in Bing. And the idea is that in those areas, both I have a pretty good performance measure of how good Bing is, that it's like the main performance measure that I use for shipping decisions. And the quality of data is much higher, because another thing that happens with these experiments is that you get a lot of flukes. So it's actually very hard to get the engineering right of all these experiments. And so a lot of experiments actually have problems in them. So this data is going to actually be audited. So I'm going to have a human RA go and call a bunch of developers and ask them, look, is your experiment real or was this a fluke? So there's a lot of effort that's going to go into making this data very something that we can trust. Because otherwise, if you find very fat tails, you could be there finding fat tails just because these results are too good to be true and are not true because there's just some fluke in the experiment. There's not going to go into super details about this, but there's this huge amount of cleaning, and you shouldn't think of this as data from like experimentation over all of Microsoft. You should think of this as of data on experimentation in an extremely mature area of a very mature cloud product. So I don't want to go for super high external validity, but I want to make sure that I'm getting correct results within what I'm studying. So this is a slide that people use at Bing at AXP to teach courses they teach. So this is what a typical experiment looks like. So here's the ads with without underlines, and here's with underlines. And in the EXP courses, they have the engineers guess which one is better. And then one of the main tenets that they have that they found out by running experiments that it's very hard to predict which ideas are good. And so basically when they play this game, they ask 3 questions, and then no one who's taking the course can ever get the 3 things correct. This is what a scorecard looks like. So the engineers can see how well their ideas are doing. There's all these metrics. The main metric that I'm going to use is called success rate. So that's roughly, basically everything that you do on the internet is being tracked all the time. And so that's kind of like, if you click on something, what's the probability that you're going to search for something, you clicked on something, and you didn't like immediately go back and click on something else or something like that. So success rate is kind of like, when did it look like it was a success? It's between 0% and 100%. This is like the scorecard. You see there's all these other metrics. This is a scorecard for the long add titles experiment that I told you about, the very historic experiment. And so you can see that someone woke up one morning in Redmond, and then they had this idea they thought was really bad, but then it turned out that this increases revenue by 13.4%, and revenue is like $7 billion. So hopefully they had a very nice epic victory dance that day. This thing here is that a few groups.
There's questions here.
Okay, so I'll try to give a couple minutes for questions. So this thing here is that some groups actually keep track of things that they triage because they do all these offline tests before things go to an online experiment. And so talking to one of them, I got this data. I got some data from a little bit of these things that are triaged offline to see, well, the ideas are getting thrown out. Are they kind of like as good as the normal ones or not? So this is what an offline experiment looks like. So basically, there's people in China who are going to rate, search results between is this better and is that better and so on. All right. So briefly, if you just take actually take a look at this data. So the first thing that you can do is just plot a histogram. So this is how much better did these ideas make Bing? Some like 1,000 ideas or so in my sample. And then basically what you see is that you have this distribution that kind of looks like a normal distribution, but not really, because if you're used to this, there's all this stuff over here that it would be just astronomically impossible that you would see those things in normal distribution. And so we're going to do some statistical tests for fat tails. So the first thing that we do is what's called a log-log plot. I'm not going to bore you with that, but it's just very clear just from the raw data that you have fat tails. And once you do some proper estimation, then basically, one distribution that fits really well is a t-distribution. And so that's just shown that that fits really well. And then the actual estimates that you get, the number that really matters is over here. This is the tail coefficient for session success rate. So it's like 1.3. So this is like way below 3. So you're definitely in the regime where you want to try a lot of stuff. And so what are the main implications of that? So there's 4 main implications. I'm not going to go over all the pictures. But so the first thing is that you want to aggressively shrink all those mediocre ideas that are getting very close to the bulk of the distribution. And so it turns out that once you shrink things correctly, so 70% of the gain, 75% of the gain or so, comes from the top 2% of ideas, which, it wouldn't look, that's just very extreme. There's this 80-20 rule that we usually talk about. This is kind of like that, but on steroids. And so basically what's happening is that if you just looked at the raw data and if you ignore the fact that you're trying thousands of things, you'd think, I'm doing a lot of kind of mediocre things that are actually adding a lot of value. And sure, those things are marginally statistically significant. It's not like they're useless, but they're just like an order of magnitude less important than what you would think if you just naively add everything up. And then the second thing that you get is that you can calculate the production function at the actual tail coefficient that you have, and it's extremely concave with this infinite derivative of 0. And so what that means is that reducing sample size actually has a very small cost. So it would actually be a very good idea to, for example, run 20% more stuff and do a lot less of this offline testing, and you could largely greatly increase productivity. One thing that you might say, but maybe the ideas that are getting thrown out are like really bad ideas. Maybe you're throwing them out correctly. And I don't have a lot of data on that, but I did show you that spreadsheet where I got some data from these offline metrics. And they seem to be, as far as I can tell, this is very limited evidence, but they seem to be not predictive at all of online performance. So for example, here's a bunch of scatter plot of the offline metrics versus each other. So it turns out they're not even that correlated with each other. So, one way of seeing before the test whether something's good, and the other way, they basically look like clouds of points. And then if I compare them to the online metrics, I see more clouds of points. So, I think it seems like you could do better by moving to this linear exploitation approach. But anyway, experiments are important. We have this new framework, the A/B testing problem, to understand how to use limited experimentation resources. And the key novelty, besides just looking more like A/B testing than, for example, bandit problems is to look at these black swans. And the best way to use experimental resources usually depends on the tail of the distribution of gains. The tail, in this case, is just a linear exploitation approach. Would be amazing. If I have time for questions, I'm happy to take them. Okay, wonderful.
Let's thank you. Do you have any questions?
Yeah, Mike.
I see you mentioned that you want to shrink the large effects less than
Yes.
small effects.
Yes.
That seems counterintuitive. It seems like if you split all your experiments in half, then the ones where you found a large effect would be like the size or the magnitude of the effect seems more likely to be off
Yeah.
to the smaller ones.
Yeah. I think like the large ones, you want to shrink them in the sense of like, did I mess up the data? And because of the engineering, did I get something wrong that just like totally messed up the experiment? Once you have ruled that out, then there's this very counterintuitive thing that actually if you find something that's like 5 standard deviations away from 0, because the normal distribution noise can't possibly get to that. So once you've determined that it's not an engineering problem, actually you really want to trust those. As opposed to I got a p-value of like 7% in my newsfeed experiment, or like 3% or something. Those you should actually be very suspicious about because you guys are doing experiments every day.
Yeah, so it's less on the effect size and more on the significance. Like
Yes.
Trust the significance more the larger.
Yes. Which I'm sure like for all of your big wins, the p-value is just like 10 to the minus, a huge amount. And so those you don't want to shrink once you determine that it's not an engineering problem.
We can maybe take one more question, but can we have the next speaker sign up?
Yeah.
How do you know the distribution if whether it's a pattern? Are you assuming that a lot of work is being done, especially
Right, so because I'm working with this very large corporation that has very good records on thousands of experiments, it's kind of easy to just go on the data, and you want to do all this careful econometrics and do this audit to make sure your data is clean, but it's kind of easy for you to analyze that data. I think, probably if you're working with a smaller company, I would kind of, be guided a little bit by the results, for example, from this paper that people have had from this big data set. But you'd be a lot more limited in like how much of your data you have to figure out your data. You probably want to use a much more Bayesian approach.
That microphone.
That's a good idea.